You are welcome to my channel. Today I'll be talking about acid-base balance, and this very presentation will form part 1 of 7, meaning we have a lot to go through. Acid-base balance, part 1. We need to maintain homeostasis. For normal or optimum body systems functioning, a lot must be in order. And one of the major examples of what must be in order is the balance between the acid and the base in the body. How can we know whether or not we have a balanced acid base or there is derangement? We can know through the clinical state of the patient. Remember, we are treating human beings, not the lab results. So, we have to consider the clinical diagnosis before ordering for any sample at all. And of course, the state of the patient. We need to know what is happening to that patient right now. Then, when we have the lab results together, we match that with the clinical state, and then we begin our interventions. We have to take the sample depending on our judgment whether or not we will need the sample. And what are those samples? We'll take sample for arterial blood gas. That is what we use mostly. But there are certain situations when and where you can use venous blood gas. For example, in circulatory failure or you are conducting cardiopulmonary resuscitation, you may use venous blood gas. You have to take sample for electrolytes, serum electrolytes. Why that? Very soon we'll get into the details of what we need it for. So we'll send all these samples to the lab, and when the result is back, when we're dealing with metabolic acidosis, we want to know what the ion gap is. And without the electrolytes that we have sampled above, we will not be able to make that determination. So you can see the clinical state of the patient, the arterial blood gas will be taken, venous blood gas could be taken under certain situations. We have to take the sample for serum electrolytes. When the result is back, we can determine an ion gap as well. The lab results are back, and what are we looking for? We're looking for the value of pH that should be between 7.35 to 7.45, and that would be normal. What about CO2, carbon dioxide or carbon dioxide? Should be between 35 to 45 millimeters of mercury, and bicarbonate ion should be between 22 to 26 milliequivalent per liter. How about the base excess? Should be between -2 to +2 millimoles per liter. And oxygen should be between 82 to 98 millimeters of mercury. Then electrolytes, we want to know the value of sodium. Most times we don't add that of potassium, but sometimes some laboratory centers will do, and then the anion gap expectation will be different. For example, if you use both sodium and potassium, and then you add the chloride and bicarbonate ions, then your anion gap will be expected to be between 10 and 20. But if you leave out the potassium, the expectation of anion gap will be between 4 to 12, and some lab will write 8 to 16. Now the pH. We will understand better, but let me lay the emphasis here right now that when it comes to acid-base derangement, we'll start making that determination whether this is acidosis, alkalosis, or compensating or not compensating based on the value of the pH. So the pH normal range is 7.35 to 7.45. On the scale is 1 to 14. pH 0 is not found in human body. So, like, I'm a physician, so I'm not looking for that. pH 1 could be found in the stomach, and that will be strongly suggestive of hydrochloric acid. pH 2 could also be found in the stomach, as indicating that there's gastric acid or lemon or vinegar. pH 3 could be found in orange or grapefruit or soda. pH 5 could be found in coffee. pH 7 is neutral, and that is found in uncontaminated water. I deliberately put uncontaminated water here because when you say water, I didn't say water just like that, because it's possible that water has been tainted or contaminated with anything. So pH 7 is found in uncontaminated water. pH 9 is found in baking soda, and pH 10 in medications like milk of magnesia. pH 13 in bleach or oven cleaner, and pH 14 in liquid cleaners. These will help in emergency room if somebody has ingested an unknown substance and you take the gastric content and you determine the pH, you can quickly take a guess about what is happening, but toxicology center will also help you. Okay, now back to pH again. We have been given the question, or the patient is before you, or the laboratory report is right here. What is the value of the pH? If it's anything between 7.35 to 7.45, that is normal. Then you don't need to bother. But anything less than 7.35, that is an acidic medium. Anything greater than 7.45 is basic or alkalotic. Now, when it is acidic and it is pointing to derangement along the bicarbonate ions, that is metabolic in origin. If the derangement is pointing to high level of CO2, that is pointing to respiratory acidosis. Base excess. From the nomenclature, that is suggestive that we are dealing with base here, whether it is in excess or not. The range, the normal range for that is minus 2 millimoles per liter to plus 2 millimoles per liter. This is the amount of acid required to restore 1 liter to its normal pH. Minus 2 is pointing to less base in the blood. And in that case, we are dealing with low level of bicarbonate, and we are heading to acidosis. Plus 2 is pointing to excess base in the blood. In that case, we are dealing with high level of bicarbonate, and we are heading to metabolic alkalosis. Negative values, for example, minus 2 or minus 1, could be found in metabolic acidosis, compensated with respiratory alkalosis. Positive values, for example, plus 2 or plus 1, is found in metabolic alkalosis, compensated with respiratory acidosis. The bicarbonate ions. Remember that bicarbonate ion is a base with the capability to mop the hydrogen ions. Anytime bicarbonate is high, hydrogen cannot be high. Then we are dealing with alkalosis. Anytime bicarbonate ion is low or it drops, then hydrogen ion will be free and rise in the blood, leading to acidosis. So, high bicarbonate is metabolic alkalosis. Low bicarbonate is metabolic acidosis. derangements. In respiratory acidosis, how do we know we are dealing with acidosis and it is respiratory? First thing first, the pH. If the pH is low, that is less than 7.35, then we know we are dealing with acidotic, condition. It depends on how low it is again. Then we want to know, is this respiratory? Then check what the value of carbon dioxide is. Some call it carbon 4 oxide. If it's respiratory, it's going to be high. And at this stage, bicarbonate will be within normal range. Then, this is a problem. This is respiratory acidosis. In respiratory alkalosis, it's still going to start with the value of the pH. But this time around, it's going to be the opposite of respiratory acidosis. The pH will be high, and the value of carbon dioxide or carbon 4 oxide will be low, while bicarbonate will be within the normal range. Okay, we've just gone through respiratory acidosis with low pH, high CO2, normal bicarbonate, right? Now, when there's respiratory acidosis with metabolic compensation, what are we going to find? Something will be slightly different. Here, the bicarbonate ions will be rising, so it will be slightly raised. Okay? Why? It will be trying to become metabolic alkalosis to neutralize the acidotic state. Do you know why? If there's metabolic acidosis or alkalosis, the respiratory system can increase ventilation to decrease CO2 or decrease ventilation to change the CO2 respectively. That could be done very fastly. But in respiratory acidosis like we have just now, the metabolic changes that will involve bicarbonate ion that is expected to be raised or decrease in alkalosis will take a longer time than the respiratory system. So it will take few days for the kidney to handle the bicarbonates to meet the compensatory threshold required. In respiratory alkalosis, it's just going to be the opposite of what is happening in respiratory acidosis. But with metabolic compensation, the bicarbonate level will drop slightly, trying to become metabolic acidosis because it is respiratory alkalosis, and then we are trying to go in the opposite direction as per metabolic compensation now to stabilize. It's like you put your weight balance on the scale. When it is high one side, you increase the weight to raise it. You just want the whole thing to be balanced. In metabolic acidosis, we're going to look at the pH first, and the pH will be low. Then we'll check the bicarbonate. What is making it low? The bicarbonate will also be low. Then we'll know this is pointing to metabolic acidosis. What will happen to CO2 if there's no compensation? The CO2 will be within normal range. In metabolic alkalosis, there will be high pH, high bicarbonate, and PCO2 will be within normal range. But if there's metabolic acidosis with respiratory compensation, something will happen. The respiratory system will help by dropping the value of CO2, trying to become respiratory alkalosis. Okay? Just to go the opposite direction. The metabolic alkalosis, on the other hand, with respiratory compensation, will give us the PCO2 they'll be rising in value, trying to become respiratory acidosis, because metabolic alkalosis is a problem. So the respiratory system is trying to adjust so that the two of them will not head towards the same direction and destroy the patient. So the respiratory system will want to become acidotic right now in the face of metabolic alkalosis, and can only do that by retaining more CO2. In mixed acidosis, this could be found in multiple organ failure or in cardiorespiratory arrest. Here we're going to find the pH to be low, which is acidotic region. The bicarbonate ion will also be low, pointing to metabolic acidosis. Instead of compensation now, when there's metabolic acidosis, that the respiratory system is supposed to be going towards alkaline region, it won't go that way. The CO2 will also be high, giving us respiratory acidosis. So no compensation here. And the two of them are heading towards the same direction, and that is bad. So in that case, we'll say there is mixed acidosis, both metabolic and respiratory. In mixed alkalosis, it will be exact opposite of mixed acidosis. But this will be found in liver cirrhosis, diuretics use, hyperemesis gravidarum, and hyperventilation. Here the pH will be high, bicarbonate will be high, but instead of compensation, having the respiratory system to give us high CO2, that is to retain CO2 to give us respiratory acidosis in the face of metabolic alkalosis, we will not get that. We will also get respiratory alkalosis with the drop in CO2. I mean, low carbon dioxide or low carbon 4 oxide. With that, I've come to the end of part 1 of 7. You may reserve your questions till part 7, because by the time we'll go through parts 1 to 7, it's very likely your questions might have been answered along the way. But if you are pressed to ask right now, please go ahead and do. You can leave your comments. Thanks for listening. Remember to share. Remember to subscribe. I appreciate it.